example. I will not talk about it, and you can practice by yourself at home. And here I already give you the solution, okay? Now, the second objective in this case is to choose a new community for expansion. So what can we do? Okay, well, pretty easy. You just look at the regression output, find the predictor that has the coefficient positive, okay? And then you will choose the communities that have large value on those predictors. So we go back to our regression output. We are using the final model. Okay. So what you can see here is that now among these three predictors, all three predictors has positive coefficient. That's good. Okay. So that means that all three predictors have positive impact on profit. Now, when you choose community for expansion, you want the community to have give you large profit, right? So you will choose the community that are high at the value of disposable income, high at the value of birth rate, and high at the value of percentage of 65 or older. But can we do that? Okay? Well, we said no, we cannot do that. That is because the relationship between the predictor is not positive. If you look at the scatter plot matrix here, you can see that the relationship between the disposable income and the birth rate is negative, okay? And the relationship between the percentage of 65 or older and birth rate is also negative. So that means that when you choose a community that are high at the value of percentage of 65 or older, that is old people, they have more, okay? Then the birth rate will be low, okay? If you choose the location that are high at the birth rate, then the percentage of 65 or older, they will be small. That is natural, okay? If a community has lots of old people, and then the community will have less young born baby, a newborn baby, right? So that is kind of a negative relationship. So it tells you that we need to trade off between the variable percentage of 65 or older and birth rate, okay? Or birth rate and the disposable income. So what can we do then? When we choose a new location for expansion, which predictor should be our priority, right? So that corresponding to rank the importance of the predictor to the response variable y. Now, we have some formal techniques, but that will be out of the scope of this course. So here we only talked about something you can rely on if you only have this output. Okay, you look at the column T, that is the test statistic. Okay, now what you do is you rank the importance of the predictor. Okay, how important is the predictor on Y based on the absolute value of the test statistic. Okay, so the larger the absolute value of the statistic, the more the impact of the corresponding predictor on the response variable Y. So now you can see that percentage of 65 or older has the largest, okay, and test statistic, followed by disposable income, and the last one is the birth rate. So that means among these three predictors, percentage of 65 or older, that means the percentage of old age people, okay, in the community have the strongest impact on profit. Increase the percentage of old age people can increase the profit the most, followed by disposable income, okay? And birth rate is the last thing you should look at. In that case, when you choose community for expansion, and then you will first find the community that are high at the value percentage of 65 or older. If two communities that are both have a very high value or at the percentage of 65 or older, the second predictor you look at is disposable income. And then you will choose the community that have large value for disposable income. Okay? You can forget about the birth rate because it has the smallest impact, and also it is negative related to disposable income and percentage of 65 or older. Okay? Now, let me summarize the thing we learned up to now, okay? And especially for this case, well, regression can be used to do lots of things, okay? And in the business field, very important application will be the interpretation part, okay? Now, for this case, it doesn't matter whether we are talking about the pharmacy profit, the retail chain profit, okay? Or it doesn't matter whether we're talking about your industry's operations profit, okay, whatever, okay, or sales. As long as you want to predict a continuous Y variable, you can use multiple linear regression. Another thing is, if you want to build a regression based on your data to find out new location for expansion for the company, okay, it can apply to all different kinds of company. What can you do? You look at your final regression result, and you identify the predictor that have positive impact on Y. Positive impact means the coefficient estimate, Bj, is larger than 0. Okay? You identify those predictor that has positive impact on Y, and then you look at the test statistic, the T value, okay? Based on the absolute value of the test statistic, you will rank the importance of the predictor on Y. Okay? When you choose new location for expansion, you will look at the most important predictor first. Okay, you will choose a location that have large value on the most important predictor. And then, if you have several locations that have very large value on the most important predictor, and then you will look at the second most important predictor, okay, and so on. So this is the way for you to identify the place for you to expand, okay? Very applicable to all fields in the business world. Another objective in this case is to identify the underperforming and the overperforming sides, okay? Now, that is also very useful because we can make use of the outlier to help us to identify those places. Outlier involves the residual. Recall that residual EI is equals to yi minus yi hat. If the residual is larger than 0, it tells you that yi is larger than yi hat. Yi is the actual value. Yi hat is the predicted value. Predicted value is the value we predict based on the regression model, or some people call it fitted value. When a residual EI is less than 0, okay, that implies that yi is less than yi hat. So let's say that the residual is much larger than 0, so I'm using 2 larger than sign to denote much larger than 0. Then yi hat will be much larger than yi will be much larger than yi hat. What does that mean? That tells you that the actual profit, in our case, okay, the actual profit is much larger than what we expected from the regression model. So the corresponding pharmacy, we can call it overperforming sign. Okay? Now, what if the residual is much less than 0? I'm using 2 less than sign to denote much less than. And then yi will be much less than yi hat. So that tells you that the actual profit for the pharmacy is much less than what we expected from the regression model. Okay? So the performance, actual performance is much worse than what we expect. In that case, the corresponding pharmacy, we call it underperforming sign. Okay? Now, you may wonder how large or how small is much larger than or much smaller than, right? Now, we learned how to identify outlier in ISO OM 2500. That is to use the standardized coefficient. So we look at the standardized coefficient. Now what we learned before is that when the standardized coefficient has an absolute value larger than 2, then the corresponding observation is an outlier. Okay, absolute value of the standardized coefficient larger than 2, then the corresponding data point is an outlier. Here, we have the overperforming side, that is the outlier at the top, and the underperforming side, that is the outlier at the bottom when we are plotting the residual plot, right? We only look at the underperforming side in this particular case. So we look at the standardized residual that are less than -2, okay? That will be our underperforming side. Now here, using the standardized residual, we identify two pharmacies, okay? One pharmacy is located in the Denver city, the other pharmacy is located in the Rockford, okay? After we identify those underperforming sites, what can we do, right? Now, you can investigate the cities that those pharmacies are located to identify the population characteristic, okay, based on the predictor in the final model, okay? So this is one way. And to find out by nature whether the profit there should be good or not, okay? And then you can look at each pharmacy individually, talk inside, to find out whether the operations management, the marketing management, okay, or the marketing strategy, whether they're good or not, okay? So that means that you need to look deep inside the pharmacy to find out whether something we can improve. If that's the best they can do, okay, we cannot improve anything. When the profit is less than 0, okay, that means you're losing money. You can consider closing those pharmacies, okay, to stop the loss from the pharmacy chain in general. Okay, so this is the thing you can look at when you identify the underperforming side. So how about the overperforming side then? Now, for the overperforming side, we can use it as the role model. Okay? Now, of course, you can also identify the population characteristic in those pharmacies, the related city, right? And if you can identify the characteristics that are similar to those population where the pharmacy are located at, then that will be the base for you to identify the location for expansion, okay? Another thing you should look at is how those pharmacies are operated, right? You can also look at the marketing strategy, the operation strategy, or the management strategy to see how they make their profit that good. You can learn from that, right? So that is the thing you can use when you encounter outlier. It can actually give you very useful implication in the business field. So that's why I told you that this case is very useful and very popular, okay, when we are talking about how to use multiple linear regression to help us extract this implication. Okay, now you can, whenever you have a profit or sales related case, okay, corresponding to multiple linear regression later on in your internship, you can always refer back to this case to look at the logic, okay? Now, let's say that we already identify a location for expansion. That is a store located in the Kansas City. We want to estimate the profit of it. Then we up to the goal for prediction. Let's say that the disposable income in this location, so this is X1 is 22,000 something. X2, that is the birth rate is 14.4. X3 is equal to 11.4. And then we can plug in, so we have the profit, right? Predicted one. And we have B0 plus B1 times X1 plus B2 times X2 plus B3 times X3. And then we can have the point estimate, okay, for the profit in this new store. That will be around 185,000. Now, point estimate usually is not very reliable because the point estimate will not be exactly equal to the true value. If they're the same, you're very lucky, okay? You can buy lottery. Well, so in practice, we will give people an interval estimate, okay? So that corresponding to how can we create prediction interval or confidence interval. Now, following, we are using the get prediction function, okay? So this get prediction function, when we operate on the our final model's output, so this model underscore fit, we use it to store the result for the final model. Dot operator followed by the get prediction, okay? And then inside we have the x value for our new observation, that is the new store. And then you will have the following output. Now on the output, the mean, that will be the y hat. Okay, or you can call it yi hat. That is corresponding to this particular new store. SE, okay, so mean SE, that is the standard error of yi hat. So that is a measure of the variation. Now the thing we can look at is the 95% confidence interval for the mean value of y given x equal to x0. Okay, so that corresponding to mean CI lower, this is the lower limit, mean CI upper, this is the upper limit. And then we have the 95% prediction interval for the individual value of y given x equal to x0. Okay, so this is the lower prediction limit. So we have OBS, stand for observation, and then OBS CI upper, that is actually the upper limit. Okay, now because some of the students told me that you totally forgot what is the difference between prediction interval and confidence interval. So therefore, I help you guys to have a quick review here using simple linear regression. So let's say that we are trying to use the house size to predict the house price. Okay, so you can see that this is a scatter plot, and we will have a straight line. Okay, so that predicts the house price. Now let's say that we are looking at the house, that the house size is equal to 1,000 square feet. Okay. Now you know that for all those houses, that the house size are equal to 1,000 square feet, they will have different house price. Okay, because the location of the house, okay, and the facing of the house also affect, okay, the house price, and also whether the house is haunted by the ghosts, okay, who knows. And then we also affect the house price. So there are variation of the house price for those houses that have exactly the same size. So if I want to get a range of the average price, so that means if I want to predict the average value of the house price, where the house have exactly the same size, equal to 1,000 square feet, okay, and then I will have a point here, okay. So to predict this point, we are using 95% confidence interval for the mean value of y, okay, given x equals to 1,000 square feet. Okay, so what we are predicting is that I'm only looking at the house where the house size is equal to 1,000 square feet. There are lots of houses, okay? I want to know on average is here, what is the house price range? Then I'm using confidence interval, okay? Now, let's say that, so the confidence interval actually will be roughly here, okay? So let's say I want to buy a house near HKUST, okay? The house size is also 1,000 square feet. Now, the house is located here, okay? And then we want to know what is the range of this particular house. Then I'm using 95%, okay, prediction interval, okay, for the individual value of y given x equal to 1,000 square feet. Right? Because I'm talking about finding the price range for that particular house. So that is the individual value of y. And then the prediction interval will be like this, much wider. Because it is more difficult for you to estimate or predict an individual value than the average value. Okay? So let's continue. Now we go back to our problem. So we are looking at that particular new store. So that is the individual y value, right? So we need to use the prediction interval then. So there's a trick, okay, in the exam. If the sentence, okay, or the question involves the term average, okay, or mean, then we are using confidence interval. Otherwise, that means individual value. We are using prediction interval. Okay, so this is the trick you can use in exam. Now, let me summarize our case and we look at the business implication. We identify 3 characteristics of the local community that can affect the profit of the pharmacies. That will be the disposable income, the age, okay, that is the percentage of old age people, and also the birth rate. Now, we find out that all 3 predictors has positive impact on Y, okay? So that means that increase the value for these 3 predictors can increase the profit. Now, we also find out that the pharmacy chain has to trade off the characteristic when they want to select a location for expansion, because they need to trade off between the birth rate and the percentage of 65 or older. So that means the birth rate and the percentage of old age people, right? Now, we find out that the old age people, okay, the percentage of old age people have the strongest impact on profit, while the birth rate has the smallest impact. So when we choose location for expansion, the first thing we look at is the percentage of old age people. Okay, and after that, we can look at the disposable income. Okay, which is the community. If the community have lots of old age people and also they are rich, then the profit in the pharmacy will be higher. Okay, so this is how you can use the characteristic of the population to help you to choose the location for expansion. And then we also make use of the outlier to identify the underperforming sites. That are the pharmacies that are located in the Denver City and the Rockford. Now, for these pharmacies, we need to identify the characteristic of these 2 cities, okay, to see whether by nature the profit, okay, in this pharmacy are not very good, okay. If by nature the profit of this pharmacy is not very good, and the operations strategy, marketing strategy, or management strategy has no problem, and the profit is less than 0, we can close down the pharmacy. If, okay, the location should have high profit, but the management or marketing or operation strategy is not good, then there's a chance for you to improve, right? Then you can intervene, right? And to learn from the overperforming side, how they operate internally in order to increase the profit of the corresponding pharmacy. Okay? Now, that will be the business implication. I always told my students, okay, especially for the students who are doing the final year company real project, whenever you look at the data, okay, don't just explore it to see what I can find out, okay? Now, you need to extract a goal. This goal needs to help the company to increase, okay, the profit or increase the sales and to add value to the company. So extract business implication is very important, okay, in the real case. And that may add value to the company and to make you an important person in the company. Now, just now we talked about prediction objective. We can use adjusted R-square to choose among different models, okay? And in practice, for some of the machine learning model, like the deep learning model, okay, they cannot calculate adjusted R-square. So how can we compare the model that we learned up to now and also the machine learning model, okay? Now, what we can do is that we can split the data into training set and test set, and then we are using the model that we build on the training set to predict, okay, the Y value on the test set. Okay? And what we do is that we are comparing the test set performance. We will choose the model that gives you the best performance on the test set. Now, in practice, we usually have an 80% to 20% split, right? 80% of the data we put into the training set. 20% of the data we put into the test set. Well, this is the usual splitting ratio. Of course, it depends on how rich your sample size is and how complicated your model is, okay? The more complicated your model is, the more the data point you need to train your model. But usually, we are using 80% to train, 20% to test. Now, let's look at the performance metrics in the test set. That will be the root mean square error. Cannot see here. So wait a minute. So let me reshare. Oh. Actually, it's the network here. It's not very good. Now, there are different performance measures on the test set. The one that we introduce and commonly used by the analytics, it will be called the root mean square error. So RMSE, root mean square error, is the square root, you have the square root here, of the mean square error. Mean square error is equal to sum of square error divided by the sample size n minus the number of predicted k minus 1. So that will be the root mean square error. Now, what we emphasize is the root mean square error need to calculate on the test set. Okay? If you are using the training set data, you can also calculate a training set root mean square error. But that will not be the one that we choose among different models when we want to find a model that gives us a good prediction accuracy. We are using the test set root mean square error. The network is not very unstable today. Okay, and I will share again. Okay, so when we are using a root mean square error, we say that the model that have a smaller root mean square error will have a better prediction accuracy. Okay, so let's say that you have 5 or 6 candidate models, and you want to choose which model have the best prediction accuracy or best prediction performance. You will choose the one that has the smallest root mean square error. Now let's look at the retail profit case. Now, the Python code here is optional, okay? I just put it here just in case later on when you want to compare the multiple linear regression result with some other model's result, okay? Now, what we do is that first we use the sample function to divide our data into training set and test set. 80% of the data will go into the training set, and the remaining data will go to the test set. In our retail profit case, 88 data points will be in the training set, while 22 data points will be in the test set. After that, we will fit 2 different models. We have the full model that contains all 6 predictors. Okay, so that will be the same that we learned in the at the beginning of the course. And then now we have the final model that only contains 3 predictors. So the thing here is we need to calculate the root mean square error on the test set. So we need to import the mean square error function from the scikit-learn library's sublibrary metric. So scikit-learn is called sklearn, okay, and in the Python. Now, so what we do is we are using the from keyword to import the from the library scikit-learn metrics. We import the function mean square error. In that case, later on, when you are using this mean square error function, you don't need to specify where it is from, okay? Directly use it like this. Mean square error. We have 2 parameters. We have the y variable and the predicted y variable. So we have the y variable on the test set. So this is the actual y value. And the predicted y value using the full model. Then we take the square root. SQRT is the square root function. And it's from the NumPy library. We take the square root of the mean square error, and then we have the root mean square error for the full model. Same thing, okay, we are using the mean square error function to calculate the difference between the actual y value on the test set and the predicted value on the test set for the final model. Okay, we have 2 models. And then we take the square root, and we will have the root mean square error for the final model. Now, let's compare the result here. What you can see is that the root mean square error for the final model is smaller than the root mean square error for the full model. So final model will have a better prediction accuracy because it has a smaller root mean square error. Okay? So up to now, you've learned two different methods to choose the model, okay, when your objective is prediction. For the first method, adjusting R square, we don't need to split our data into training and testing. Now, let's say this is the data available to you. You use all of the data available to build model. Okay? You can use all the data available to you to build several models, and you compare the adjusting R square. You will choose the model that has the largest adjusting R square. Okay, so this is one way for you to choose model. Now, the second method will be using the test set, root mean square error. So again, this is the data available to you. What you need to do is you split the data into two parts. We have the training set, we have the test set. We use the training set to build different models. And we calculate the root mean square error on the test set. And then you will compare the root mean square error on the test set. You choose the model that gives you the smallest test set root mean square error. Okay? So that will be two different ways for you to choose the models, okay, when the objective is to do prediction. So let's look at the summary, okay, from this topic. We are mainly talking about the procedure for multiple linear regression. So this is a review. So at first, we need to plot scatter-plot matrix, okay, and that will amount the predictors and the response variable y. You want to find out whether there are linear relationship between the predictors and the y. So this is the first thing you look at. The second thing you look at is whether the predictor x themselves are highly related or not, because it may give you some idea whether we have multiple linearity problem. The third thing we look at is outlier, okay? Because using scatter-plot matrix, it may help you to identify the outlier. The outlier may be typo, something you need to delete, okay, or correct. The outlier may also give you useful information if the outlier is the actual data point, okay? You may make use of it. After that, we fit the model, and then we will check the model assumption. Recall that the model assumption is involving the random error term. We say epsilon I is IID normal with mean 0, variance sigma square. Okay, so here we have 4 assumptions. Now, you need to check those 4 assumptions using the residual plots. Okay, different residual plots can be used to check different model assumptions. If the model assumptions are violated, then you need to deal with it, okay, before you continue. So how to deal with it? Say for example, you are using transformation. Say for example, originally you have the y variable, you keep the log of y, so this is the log transformation, okay? And then let's say the model assumption now they are satisfied, we continue to conduct hypothesis testing. The first test you look at is the F test. Okay, we want to use it to verify whether the model as a whole is useful or not in the population. Okay, so if the p-value in this test is less than alpha, alpha is the significance level, usually choose to be 0.05, then we will reject the null hypothesis at 5% significance level. And then we can conclude that the model is useful. If the model is useful, we further on interpret the R square. Okay, R square tells you how useful is the model in the sample, in this particular data set. Okay, so if the R square is larger than 80% or equals to 80%, that means the model is very good already. But usually you will not have the R square that high. Okay? If the R square is larger than 80% or equal to 80%, then that means your model is already very good. Otherwise, you may find way to fit the data better. Okay? But if your objective is to interpretation, R square is not that important. Okay? Prediction may be better. Now, if the model is not useful, then you don't need to continue. Okay? You can abandon the current model and find some new predictor to build new model. So now let's say that the model is useful, Then if your objective is to do interpretation, then you can check the VIF to find out whether there are multiple linearity problems. So VIF larger than 10, that means the corresponding predictor has multiple linearity problem. When there's multiple linearity problem, you need to deal with it either by deleting some redundant predictor or combine those highly correlated predictor into one variable. Now let's say that we already deal with multiple linearity problem, then we can continue to look at the predictors to find out which predictor are useful, okay? So this is the t-test, or we call it individual t-test. We look at the p-value. If the p-value is less than alpha, we will reject the null hypothesis at 5% significance level. Alpha usually choose to be 0.05. And then we can conclude that the predictor xj is useful to predict y. Now for this test, the null hypothesis is to test beta j equal to 0, and the alternative is to test beta j not equals to 0. Now let's say that we identify some predictor are useful to predict y, some predictor are not useful to predict y. Then for those predictors that are useful to predict y, you can interpret the coefficient estimate bj and also the confidence interval for the beta j. Okay, to tell people what is the impact of that predictor on y.